All right, calculus class, let's look at an example of trig substitution. So what we've previously done in integrals that look like this is we've used like the tables, and that's been fun. We were learning to use the tables on those. But if I say, evaluate the following integral and specifically say use trig substitution, then you need to be able to do it this way, okay? So if you look, we've got a number and a squared variable. So it's typically a perfect square. It's not always. Like we've seen stuff like 7, right? And that's the square root of 7 squared. So any number can be in here. But a lot of times, especially early on, it'll be perfect squares. So when we look at that and we see the squared variable following the minus sign, notice that looks like this very first one, and that's the substitution we're going to make. So we're going to say that x is equal to what is being squared here is 5. So 5 times the sine of theta. Okay, so there's how we set that up. Now, there's a couple of different paths you can go here. You can substitute or you can use trig. All right, I'm going to show you both, but first I'm going to show you the substitution step. So if I use substitution, I would replace x with 5 sine theta. All right, and then dx, the derivative of this is going to be 5 cosine theta d theta. And I'm going to replace that with the numerator. All right, and then the last thing that we need to substitute here are the variables. So x is 5 sine theta. These are x's, okay? This is x equals. Okay? So x is 0, so that means that sine theta is also 0. So what makes the sine of theta 0? When theta is 0. So this lower interval is 0. Again, now we're doing theta equals. Okay, we're substituting, so we're switching x's for thetas. All right, the other one we got 5 sine theta equals x equals 5 halves. All right, so 5 sine theta equals 5 halves. What makes sine of theta equal 1 half? I'm dividing both sides by 5. So that is theta equals pi over 6. So that makes this upper value pi over 6. All right, and now we're ready to simplify this denominator and do the integration. So this is going to be 5 cosine theta d theta, but on the bottom we're going to have the square root of 25 minus 5 squared is also 25 sine squared theta. All right, 25 is common here, so I can factor that 25 out. It comes out as the square root of 25, and then we're multiplying that by, if I factored this out, I would have a square root of 1 minus 1 sine squared theta, or 1 minus sine squared theta. All right, notice the numerator is still 5 cosine theta d theta. The denominator is 5, and then 1 minus sine squared, well, that's cosine squared, and then this is the square root of that. So technically, again, that's the absolute value of cosine theta. But in 0 to pi over 6, that's that on the unit circle, cosine, which is the x-coordinate, is positive. So we don't have to worry about absolute values. And notice everything's going to cancel here except for just the d theta, obviously. So we end up with just 0 to pi over 6 d theta, and the integral of d theta is just theta. All right, plug in pi over 6, plug in 0, subtract, you're just going to get pi over 6. And that is our area underneath this curve. So that's our first example of a trig substitution. Now let's look at it with trigonometry rather than substituting the values after we make that declaration of what x is going to be. All right, now this is the same startups because we see the squared number minus a squared variable. It's going to be that. It's going to be our setup is still going to be the same. It's going to be x equals a, or again, in this case, 5 sine theta. Now we're going to use trig. So what I'm going to do here is solve for sine, and I'm going to say that's equal to x divided by 5. And if you remember with trigonometry, with your right triangle trigonometry, sine is defined as opposite over the hypotenuse. So I draw a right triangle. I declare where theta is. So theta is there. The opposite of that angle is over here. That's x. The hypotenuse is opposite the 90 degrees. So that's this side here. That's 5. And then what does that leave the other side to be? Well, the Pythagorean theorem says that that's 5 squared, or 25, minus x squared. And there you see the denominator show up. Okay, if you set these up correctly, the denominator will show up when you do these. Now, the numerator is just 1, so what I'm going to do here is use the hypotenuse and this adjacent side in a fraction. So 5, the hypotenuse, over the square root of 25 minus x squared is hypotenuse over adjacent. And if you recall, that is the secant of theta. Okay, now we still need to get dx, so we still need to do the same thing that we did before. So dx is equal to 5 times the cosine of theta. So that's still going to be a process no matter which way we do it. Okay, now we don't have 5 here, right? All we have is 1 in our original. Okay, so what we're going to do is say that 1/5 secant theta is 1 over x, 25 minus x squared under the radical. So this in green becomes 1/5 secant, and then dx we see is 5 cosine theta, d theta. And then the exact same thing that would happen before with the changing of the limits integration would happen. And then secant and cosines cancel, 1/5 and 5 cancel, and we end up with 0 to pi over 6 of d theta again. Okay, so it's going to be the exact same work eventually, or you're going to get the same thing no matter which way you go about it. But we arrived at our substitution via trigonometry rather than via algebraic substitution and manipulation. All right, both of them will work though.